In our previous lecture, you have seen the discretization of one-dimensional transient diffusion equation using explicit scheme. Here, you will see implicit and Crank-Nicolson schemes. Recall our discussion on explicit scheme. In explicit scheme, what we did is this right side of this diffusion equation, that is alpha del 2t del x2, we discretize that at nth time level. In implicit scheme, on the other hand, we are discretizing the right hand side, as you can see here, at n plus 1th time level. The truncation error in this case also remains of the order of delta t delta x squared. The discretization of the left hand side, that is the temporal derivative, remain unchanged no matter we are having implicit or explicit scheme. So now take a close look. T n plus 1 appears both sides of the equation. So if I arrange this and if I take t n plus 1, everything on left side, and t n are right side, then my equation looks like this: r ti minus 1 n plus 1 minus 1 plus 2 r ti n plus 1 plus r ti plus 1 n plus 1, where r is this alpha delta t divided by delta x square. Now if you look at this equation, you will see that the left hand side we have all three unknowns, ti minus 1, ti and ti plus 1. All of them are at n plus 1th time level, and therefore they are unknowns, or they are the new t. The old t, that is the nth time level, that we already know, that is coming here at the right hand side. So if we look at the stencil here, let's say this line represents the nth time level. Then as I go from n plus n to n plus 1th time level, then this n plus 1th time level is totally unknown. This red point is of course the I point, and we have left side we have I minus 1, right side we have I plus 1. Nevertheless, all three of them are unknown because they are at n plus 1th time level. So think about that we are marching in the direction of time in this stencil, and the x direction is here like horizontal direction. So now that we have, if we compare with the explicit scheme, we were having only one term that was at n plus 1th time level. Everything was at nth time level. So the calculation was super easy. Everything was known in each equation, only one unknown. That means that was not solution of equations as such. That was simply calculations. But now we have a problem here. We can see that every equation has three unknowns, and let us say we have m number of grid points in x. So we have at n plus 1th time instant, if we have this m grid points, we have m equations and m unknowns. For every equation, for every point I write this equation. So, and every equation contains these three unknowns. So we at the end we have this m equation, m unknown system. Nevertheless, each equation can have at max three unknowns, and you can see one unknown is just before this I, another unknown is just after this I. So it gives us a very familiar structure, that is the tridiagonal system of equations. This is a very nice thing because we already know how to solve the tridiagonal system. So let us take an example here. So our equation inside the domain turns out to be of this type, that is r ti minus 1 n plus 1 minus 1 plus 2 r ti n plus 1 plus r ti plus 1 n plus 1 minus ti n, where r is this alpha delta t by delta x square. Of course, we have certain initial condition, and let us say the initial condition is t equal to t2 and boundary condition between x equal to 0 to x equal to L. Both boundary we have, let's say, temperature at T1. These are of course arbitrary at this point. We are not considering so much about what happens with the initial or boundary condition, but we will see that how to set the algorithm to solve these equations, to solve the partial differential equation. In this case, of course, we can see the initial temperature is T2, and if we set both the boundaries at T1, eventually the solution will reach steady state, and at steady state temperature everywhere will be T1. You can check that by solving it and by playing around with it. So let us now take, for instance, n equal to 0. So for n equal to 0, we have n plus 1 to be 1. That means n equal to 0 means that is the initial condition. Time level 0 is initial condition. So Ti 0 is T2, that is the initial condition. I start from there and then I go to Ti 1. This 1 as superscript is the time level. Time level 0 is initial condition. Time level 1 I am calculating here. And at time level 1, I know that both the boundaries will be at T1. So here at I equal to 1, I equal to m, both are at T1. And in between, I2 to m minus 1, this governing equation will be applicable. That means r ti minus 1 at time level 1 minus 1 plus 2r ti at time level 1 plus r ti plus 1 at time level 1. And on right side, I have ti 0, which is coming from the initial condition. So this is known. All three ti I minus 1, I plus 1 on the left hand side are unknown. But now we can use this Thomas algorithm once again. We know how to do it. We solve it. After the solution, I get the Ti1. This is not a steady state solution. This is only the solution we have taken one time step. That's it. So once we have this Ti at time level 1, we can use this as our known information, and I wish to find what would be the Ti at time level 2. So I come down to n equal to 1. That is my old information. And at time level 2, my boundary conditions remain still at T1. But at the inside, I have the same equation. This is r Ti minus 1. This is time level 2. This is not square. Please don't get confused with these are square. These are not square. These are only time level 2. Here also minus 1 plus 2r Ti2. These are time level. And r Ti plus 1 and 2, which equals minus Ti1. Here again r is alpha delta t by delta x square. We can once again use tridiagonal matrix solver to find Ti at time level 2. So you can see that from one time level to next time level, as we progress, we have to use this TDMA at every time level. So the previous problem that you have solved in exercise 1, that was steady state heat conduction problem, where you have solved this tridiagonal matrix solver, this Thomas algorithm you have used only once, and that was it. Here it is not so. Here at every time level you have to solve this tridiagonal matrix once, and depending upon the physical problem, to reach steady state you may have to take many thousands of time level. So at every time step you have to solve this. That means many thousand times you have to solve this TDMA. So now you understand that your TDMA solver must be very good, very fast, otherwise this entire solution will take a lot of time and lot of resource. Now we move forward and we look at this Crank-Nicolson scheme. Crank-Nicolson scheme is essentially half of implicit. So what we do on right side, in implicit I take discretization at n plus 1 at time level, and explicit I take n time level. In Crank-Nicolson scheme I take half of explicit plus half of implicit. So essentially this del 2 t del x2, that is taken as alpha by 2 del 2 t del x2 at n plus alpha by 2 del 2 t del x2 at n plus 1. So you can clearly see here that if I take all this n plus 1th on left side and nth terms on right side, then left side I have this, keeping this r equal to alpha delta t by delta x square. On left side I'll have r by 2 ti minus 1 n plus 1 minus 1 by r ti n plus 1 r by 2 ti plus 1 n plus 1. On right hand side I have minus r by 2 ti minus 1 n minus 1 by r ti n minus r by 2 ti plus 1 n. So left hand side is completely known, right hand side is completely unknown. If we look at the stencil now, you can see that this stencil looks sort of similar to implicit. Here at n plus 1 at time level we are dealing with 3 unknowns, and each equation has 3 knowns at nth time level. In case of purely implicit, we had only 1 known at nth time level. Here we have 3 known quantities in each equation at nth time level. So how we are going to solve it? It looks like that if we have n number of grid points, then at n plus 1th time instant we have m equations and m unknowns. However, each equation has only 3 unknowns. Therefore, once again, we have a tridiagonal system of equation. So the way we are solving the implicit problem, the same way we can solve the explicit problem here. The only difference is that the coefficient of the tridiagonal matrices will be different between implicit and Crank-Nicolson, but otherwise the procedure remains same. So let us see how it is. Taking the same problem, del t equals alpha del 2t del x2 with an initial condition of t equal to t2 and boundary condition t equal to t1. So we know that here at the end, if I run this case, in long time temperature everywhere will come down to T1. But how we run the case, let us check. Here the initial condition at time level 0, that is T2, and then I take n equal to 0. As I take n equal to 0 at the boundary Ti1, this 1 is time level, and I equal to m, I equal to 1, once again Ti1 is T1. These are set by boundary condition. Interior points, that is 2 to m minus 1, we have to satisfy the governing equation we just derived, that is r by 2 Ti minus 1 n plus 1 minus 1 plus r Ti n plus 1 plus r by 2 Ti plus 1 n plus 1. And right hand side, everything is at nth time level, so everything should be known. We therefore find tridiagonal matrix solver to get this Ti at one time level. And then, as we are doing in the implicit problem, we will march in time. Same procedure we will follow, and we will get the solution for n equal to 1. The same idea as in implicit, so we have to use this TDMA once in every time level to march forward. So if we are taking thousands of time step marching, then thousands of time we have to solve tridiagonal matrices. This is not going to be easy, but in your homework you will try this idea that how you can solve tridiagonal matrix at every time level. You can now take a small exercise and list the possible advantages and disadvantages of implicit scheme, and also calculate the truncation errors of explicit, implicit and Crank-Nicolson scheme. You will probably find Crank-Nicolson scheme to be relatively more efficient than the others. This is a good time you take a look at chapter 3 of your textbook and study explicit, implicit and Crank-Nicolson method for 1D transient diffusion equation. Thank you. That's all for this lecture. I'll see you in class.